So I'm going to do that on another piece of paper here. So we'll say Model 5 rate laws. Okay, so you notice that I've got it as 2A. I added some stoichiometry to this to make this a little bit more interesting. 2A goes to 2B plus C. And so here we're going to assume this is an elementary step, which I haven't talked about yet. But basically what that means is with elementary steps, the stoichiometry does give us the reaction order. Okay, and I'm going to talk about that next, but for now we're just going to go with this example. Okay, so now how do I get the rate law for everything? Well, I'll first start by just following our process by saying negative 1/2 dA dt. Okay, equals. And it's all about the reactants, right? So I only have one reactant, so that's going to be K times A. And in all of these models, you can assume these are elementary steps, which means the stoichiometry does give me the reaction order. And so that means it's K times A squared. Okay. And now this is the only reaction involved in A. So that's it. That's the rate law for A. So I could now, what I'm going to do here, okay, I want to keep this in terms of dA by dt. So I'm going to call that negative 2 times Ka squared. All right. And so now with B is going to be positive 1/2 dB dt. And that is actually still going to equal K times A squared because it's all about the reactants. And so what this means now is dB by dt equals positive 2K times A squared. And that makes sense because the stoichiometry, they both have the same stoichiometry. They should be equal and opposite rates. And then finally, C is just going to be positive dC by dt also equals Ka squared, right? But now that just remains as dC dt equals positive K times A squared. So what we can see is A and B will be produced at a rate that's twice as great as C. And that's what I did right here in my model, in the ND solve portion of my model. Look, there's A of prime t equals negative 2 Ka times K squared. B prime equals 2 times K times A squared. But now C just equals K times A squared. And look, this is what we get in the model, right? You can see that twice the amount of B is created as C because of the stoichiometry. So make sure you're getting the stoichiometry correct. That's really important. All right? And then now to do this manipulate model, this is going to be hairy for a lot of you. So we recognize here I put in Ka and I put Ka for the Arrhenius is A times the exponential of negative EA divided by RT, where I've got values for R. Well, R is going to stay the same, but I've got values for TA and EA. So now to make a manipulate out of that, like I did here, right? I go manipulate, plot, evaluate. And again, we're going to evaluate this for A, B, and C. And then we're going to replace those evaluations with the ND solve model. But now check out what I do. A prime of t equals negative 2. And then look, this whole chunk right here is K. So we're putting the Arrhenius equation directly into that model. So there it is, K times A squared. And then here's B prime of t equals 2 times, once again, K times A squared. Okay, and then C, I don't have to have the 2, right, because of the stoichiometry. And then now, look, on my manipulate model, I'm going to vary A, the frequency factor. I'm going to vary the initial concentration. I'm going to vary the activation energy. And I'm going to vary the temperature. And what I recommend, because it's 1 over temperature, that is why I did not start at 0, as I can't do 1 divided by T. You can definitely start the activation energy at 0. That's fine. And I also did not start the pre-exponential factor at 0 either, although I suppose I could have. Okay, so that's how I get this model. Pretty cool stuff. Okay, where now what's happening? Why is this? Oh yeah, I froze the reaction out. So, and you can see this is also a very fast reaction based on the rate constant, right? 10 microseconds. But again, that gives you this idea, right? That, you know, at room temperature or at 100 Kelvin, I know that was a wild value. So let me start over. For 19 kilojoule, room temperature is definitely sufficiently high to make this react over like 1 microsecond. Okay? But for that same 19 kilojoule activation energy, at 100 kilojoules, it's not, or at 100 Kelvin, it's not changing. All right?